Hello everyone. Today we continue with the theory of indicators. Important theories of indicators. Okay. First of all, we have to understand what is an indicator. An indicator is a substance which is used to determine the end point in a titration. End point in titration. So what do you mean by end point? When we go on adding base to the acid, at one point neutralization process takes place. Neutralization of the given acid will occur by adding certain quantity of base. That point where the acid base neutralization is completed is called what? End point. End point. And titration is what now? Titration is between acid and base. That is called acid base titration. So to determine the end point of a titration between acid and base, we use a substance called indicator. Okay. So in acid-base titrations, organic substances such as weak acids and weak bases, certain organic weak bases and organic weak acids are generally used as indicators. So what are indicators here? Organic acids or organic bases. Most of the organic acids and bases are what? Weaker in nature. So actually what here? Actually organic acids are weaker. But if you take sulfonic acid is what? Strong acid. Okay, remaining acids are what? Weaker acids. Is that clear? So generally, organic weak acids and organic weak bases are used as indicators. They change their color within a certain pH range. In a certain pH range, the indicators will be changing their color. Okay, the color change and the pH range of some common indicators are given below. Here. So next here, some of the indicators given here: methyl orange, methyl red, litmus phenol red, phenolphthalein. See spelling here: phenolphthalein. So phenolphthalein, phenol red, litmus, methyl red, methyl orange. So these all are what? No, different types of indicators. So every indicator has certain pH range. pH range will be there here. Suppose you take methyl orange. The methyl orange has the pH range between 3.2 to 4.5. And the color change is what? Pink to yellow. The color change will be pink to yellow. That means what now here? In basic medium, it will be yellow in color. In acidic medium, it will be red. Actually, pink means red. So it is pink given here, red it is. Like that, the color change will be observed here. And methyl red, litmus, phenol red, phenolphthalein. Mainly we use what? Methyl orange and phenolphthalein. A phenolphthalein indicator has the pH range of what? 8.3 to 10.5. And the colorless changes to pink color. Actually, in acidic medium, the phenolphthalein has colorless nature, but it will be turned into pink color in basic medium. Phenolphthalein color in basic medium is pink. Phenolphthalein acidic medium is colorless. And methyl orange in basic medium yellow, and methyl orange in acidic medium red. Actually, not pink, it is red. Okay, so different indicators, just you go through later. I will send the table. Now, theory of acid-base indicators. So there are two theories. Okay, two theories have been proposed to explain what? The change of color of acid-base indicators within a pH range. Okay, so with change in the pH value, of indicators, there will be change in color. With the change in pH value of indicator, the color will be changing. First theory is that Ostwalds theory. Okay, of acid-base indicators. So first one is what? According to this theory, first point what we have to understand is that the color change is due to ionization of the acid-base indicator. The color change is due to what? The ionization of acid-base indicator. Okay, so due to ionization means breakdown into ions. Okay, the molecule will be broken down into ions. That is called ionization. So the color change is due to what? Ionization of the acid-base indicator. The unionized form, that is the unionized molecules. The unionized molecules or molecular form has different color than the ionized form. The the unionized form will be having different color. That point we have to understand. Means the undissociated molecule will have one color and dissociated ions will have the other color. That point we have to understand. And next point is that the ionization of the indicator is largely affected in acids and bases, as it is either a weak acid or a weak base. If indicator is weak acid, it will be dissociated in basic medium. If indicator is a weak base, it will dissociate only in opposite medium, that is acidic medium only weak base will dissociate. In basic medium only weak acid will dissociate. In case the indicator is a weak acid, suppose its ionization is very much low in acids. The weak acids will dissociate very less in acidic medium due to common ion of H plus ions. Due to common ion effect of H plus ions, weak acids will dissociate very less in acids. While it is fairly ionized, it means what here weak acid. This weak acid is fairly ionized in alkalis. Alkalis means soluble bases. In soluble bases, the weak acid indicator will be dissociated. But the same weak acid indicator is not dissociated very much in acids due to common ion effect. Similarly, if the indicator is a weak base, its ionization is large in acids, opposite medium, and low, the ionization will be low in alkalis bases due to common ion of OH minus. In alkalis, OH minus is there. In this weak base indicator also OH minus there. Due to common ion effect, the dissociation, that is ionization of weak base indicator will be very low in basic medium. That point we have to understand. Considering two important indicators, phenolphthalein, a weak acid, and methyl orange, a weak base, Ostwalds theory can be illustrated as follows. Ostwalds theory can be explained as follows. First one, phenolphthalein. It can be represented as a HPH. H plus ion, pH minus ion, capital P, small h minus. It ionizes in solution to a small extent, as what HPH undissociated molecule dissociates into H plus and pH minus. The undissociated form, that is molecular form, has colorless nature, and the dissociated ion has pink color. Anyhow, H plus will be colorless. pH minus has what? No pink color here. Means phenolphthalein negative ion. The negative ion of the phenolphthalein molecule has what? Pink color. On dissociation only it will convert into pink. Okay. Otherwise it will be colorless. The original nature of phenolphthalein is what? Colorless nature. But it turns into pink in basic medium only. In basic medium only, this weak acid will dissociate. That's why the color of phenolphthalein in basic medium is what? Pink. In acidic medium, dissociation will be very less. That point we have to understand. Next, applying law of mass action, the dissociation constant, ionization constant is equal to the concentrations of products by reactants. So H plus ion concentration into OH means pH minus ion concentration divided by undissociated molecular concentration. Okay. Next, the undissociated molecules of phenolphthalein means HPH molecules are colorless. The molecules are colorless. While pH minus ions, the negative ions of phenolphthalein, are pink in color. In presence of an acid, the ionization of HPH is practically negligible. Why it is negligible? The ionization of HPH in acidic medium is negligible. Why? Because of common ion H plus. In acidic medium, H plus will be there. In HPH dissociation also H plus will form. So because of which clear means because of common ion effect, the backward reaction will be favored here, and HPH dissociation will be reduced. Okay, as the equilibrium shifts to left hand side due to high concentration of H plus ions in acidic medium. In acidic medium, H plus ions will be more. That's why the backward reaction of this dissociation will be favored according to Le-Chatelier's principle. Backward reaction will take place. That's why undissociated molecules will be increasing in number. Thus, the solution would remain colorless. Undissociated molecules will have which color? Colorless. no color. On addition of alkali means when base is added, soluble base is added, the hydrogen ions are removed by OH minus ions. In the alkali, what will be there? OH minus will be there. These OH minus ions of alkali will take away H plus ions. Okay, when H plus ions are removed, common ion effect will not be there for this HPH, na? For the HPH, common ion effect won't be there. That's why the dissociation will increase. In basic medium, what happens when we add alkali? What happens in basic medium? HPH dissociation will be more. More dissociation means more pink color. Intensity of pink color increases. In basic medium means alkali medium. Shifts the reaction towards the right hand side. Thus, the concentration of pH minus ions increases in solution, and they impart means they give pink color to the solution. When does phenolphthalein give pink color in the solution? If it is acidic, basic medium or acidic medium. In basic medium, phenolphthalein imparts which color? Pink color. Let us derive Henderson's equation for indicators. Already for buffer solutions, we have understood now Henderson's equation. pH of buffer solution is equal to pKa plus log of salt concentration by acid concentration. So like that, the same type of Henderson equation can be applied for indicators also. Now HIN is what? Indicator. Phenolphthalein, indicator, or some indicator is taken. IN minus is the negative ion of indicator. H plus is hydrogen ion. H plus and IN minus. It is acid form. As it is ready to produce H plus, it is what? Acidic form. So the acidic indicator is taken. When we add to the water aqueous solution, now H plus will be produced here. The H plus will be taken by H2. Now H2 oxygen has what? Two lone pairs here. The two lone pairs will accept what? H plus. That's why the H2 acts as what? Proton acceptor. Proton acceptor is what? Bronsted base. Bronsted base H2. That's why H plus will transfer here like this. Now H2O becomes what? H3O plus. HIN molecule becomes what? IN minus. So this IN minus is what? Conjugate base of HIN. IN minus is what? Conjugate base of what? HIN. So it is acid form we take. This one we take base form. And this pair is what now? Conjugate acid base pair. Okay, ma. Next, KIN means what? The dissociation constant of indicator. Indicator is nothing but weak acid only. So here Ka only. Ka means what? Dissociation or ionization constant of indicator is equal to products concentrations by reactant concentration. So products concentrations by reactant concentration. Why H2O is not mentioned here? The H2O is taken large excess. When H2O is taken large excess, water is taken large excess, its concentration does not affect what? KIN value. That's why H2O is not taken here. So we have taken concentration of IN minus ions into concentration of H3O plus, that means H plus ions, by concentration of indicator molecules. It is nothing but concentration C, concentration of indicator HIN. Okay, here KIN is what? Ionization constant of indicator, dissociation constant of indicator. Now from that equation, H3O plus concentration, that is the H plus ion concentration, is equal to KIN into HIN by IN minus concentrations. Now here, what is H3O plus concentration? Here H plus concentration. Now we can take logarithm, generally logarithm, what here? Logarithm of negative logarithm of H3O plus concentration, nothing but pH. We know this. pH is equal to negative log of minus log of H plus concentration, otherwise H3O plus concentration we take. That is equal to minus log of KIN in place of H3O plus. What we can substitute now? In place of H3O plus, we can substitute this one. KIN, HIN by IN minus. So log of minus log of KIN minus, okay, this one. By here, generally what here? Log A by B is what now? Log A by B is what? Log A minus log B. Log A minus log B we take here. So we take this concept as what now here? pH, calculation of pH here. Now, pH is equal to pKIN. pKIN means what? Minus log of KN. Minus log of KIN is nothing but pKIN. P power Ka. Like that, P power KIN. minus log of KIN value is equal to pKIN plus log IN minus concentration by HIN concentration. So this equation is called Henderson's equation. The derivation part you don't require. Okay, first directly take a pH value. pH value of what now? Acidic indicator. The pH value of weak acid indicator is equal to P power KIN plus log indicator ion, negative ion concentration by indicator molecule concentration. Okay, in previous case, what we have taken log salt by acid we have taken. Here log IN minus indicator by HI concentration. Sorry. So this is what now here Henderson's equation for our indicators. Now at equivalence point means at end point. Whenever end point occurs here at equivalence point, the HIN concentration and IN minus concentration will become equal. These two concentrations become equal at what? Equivalence point. At end point, what two will become equal? IN minus becomes equal to HIN. Then log 1 it becomes log 1. Log 1 value how much? 0. Then 0 plus pKin, pKin. Then pH is equal to pKin it will be. pH is equal to pKin. So pH is equal to pKin if IN minus concentration is equal to what? HIN concentration. So this equation you know down. So write down this equation. pH is equal to pKin plus log of IN minus concentration by HIN concentration. Where pKin is nothing but minus log KIN. Minus log KIN. Next, methyl orange, another indicator according to Ostwalds theory again. Methyl orange itself is what? Weak base, weak organic base. So it is a very weak base and can be represented as what? MEOH. MEOH is what now here? Methyl orange. So it will give what now? Me plus and OH minus. So it is ionized in the solution to give Me plus and OH minus. Okay, so it is reversibly ionized because it is weak base now here. And what is the original color of this methyl orange here? Yellow. But after dissociation, it will give what? Cation. The cation of methyl orange will have which color? Red color. Where does it dissociate generally? In basic medium or acidic medium? In opposite medium. It is itself base now. So in opposite medium indicates what? In acidic medium, it will dissociate into cation and OH minus. OH minus is colorless and Me plus cation of methyl orange is what now? Red color. So color of methyl orange in acidic medium is what? Red. Okay, applying law of mass action again, K is equal to what? Dissociation constant or ionization constant is equal to product's concentration by reactant concentration. So in presence of an acid, OH minus ions are removed. In presence of acid in acidic medium, what happens now? OH minus ions of this indicator, this OH minus will be removed by acidic medium. When OH minus removed from acidic medium, in acidic medium, now balanced equation will be favored in which direction? Forward direction. In forward direction, it will be taking place. More dissociation takes place because OH minus removed by acidic medium. So in presence of an acid, OH minus ions are removed in the form of what? Water molecules. H plus and OH minus combine to form water molecules. And the above equilibrium shifts to the right side, right hand side. The sufficient Me plus ions are produced which give red color to the solution. The Me plus ions will give what? Red color to the solution. On addition of alkali, suppose now, to this acidic solution, we are adding what? Alkali. When we add alkali, soluble base, the concentration of OH minus ions increases. Concentration of OH minus ion increases means what? Backward reaction takes place. Backward reaction takes place because OH minus added here. When we add base, OH minus will be added now. Because of addition of OH minus, backward reaction takes place. Means the dissociation of methyl orange will decrease. Okay, then left hand side the reaction will be favored. That is, the ionization of methyl orange is practically negligible in which medium? Basic medium, because of common ion effect of OH minus in basic medium. Thus, the solution gets the color of unionized methyl orange molecules, that is yellow color. The molecules have yellow color, the Me plus ion has red color. Like this, methyl orange imparts red color in acidic medium only. In basic medium, it gets which color? Yellow color, its own color. This theory also explains the reason why the phenolphthalein is not suitable indicator for titrating a weak base against strong acid. Okay, when titration is between weak base versus strong acid, we cannot use what? Phenolphthalein, because phenolphthalein is itself what? Weak acid. So this weak acid cannot be used in the titration of weak base versus strong acid. The reason is that this weak base will produce very less number of OH minus. Na? Weak base will produce what? Very less number of OH minus. That number of OH minus, less number of OH minus will not be sufficient to remove H plus ions from phenolphthalein equilibrium reaction. From the equilibrium reaction of phenolphthalein, H plus cannot be removed by OH minus ions of this weak base. That's why the phenolphthalein cannot be used as suitable indicator in the titration of a weak base versus strong acid. That point is understood. Next, the OH minus ions furnished by weak base are not sufficient to shift the equilibrium towards right side, means towards the product side. That is, pH is not reached to 8.3. The pH will not be reached to 8.3. Thus, the solution does not attain pink color. The solution does not attain pink color. Similarly, it can be explained why methyl orange is not suitable indicator for the titration of weak acid versus strong base. Here for weak acid, when weak acid is involved, methyl orange cannot be used because methyl orange is itself weak base and here weak acid is used in titration. This weak acid will produce very less number of H plus. Weak acid will produce what? Very less number of H plus. That H plus ions produced by weak acid will not be sufficient to dissociate methyl orange. Okay, when dissociation of methyl orange is not happening in weak acid, it cannot be used as what? Suitable indicator. In first of in the beginning, one of the tables we have discussed, every indicator has its own pH range. In that pH range only it will act as indicator. If the pH range is not reached, that indicator is not suitable for that titration. We have to understand. So tell me now, when weak acid versus strong base titration is taken, we cannot use methyl orange as suitable indicator. When we take weak base versus strong acid titration, here we cannot use phenolphthalein. Phenolphthalein is weak acid. Here for weak base, we cannot use this one. Okay, that point we have to understand. Next, and also remember, if we take weak acid versus weak base, the titration between weak acid versus weak base, suppose both are weak, acid is weak, it is titrated with what? Weak base. In that case, we have to understand that no suitable indicator is available. Both are weak here. Weak acid is titrated against what? Weak base. When both are weak, no suitable indicator is available. Okay, and suppose we take strong acid versus strong base. Both are strong. Strong acid versus strong base. In that case, any indicator can be used. Any indicator can be used as suitable indicator. No particular indicator there. Anything can be used. In which case, when strong acid interacts with what? Strong base. When titration of strong acid and strong base is taken, any indicator can be used. In which case, we cannot use suitable indicator. No indicator is suitable, in which case, when weak acid is titrated against what? Weak base. When we use phenolphthalein, If weak acid is titrated against strong base, weak acid versus strong base, the phenolphthalein can be used. Because phenolphthalein is weak acid, here weak acid is there in the titration process. So for the titration of weak acid versus strong base, what is suitable indicator? Phenolphthalein. And when weak base is titrated against strong acid, weak base versus strong acid, in that case, methyl orange can be used. Methyl orange is itself what? Weak base. So when weak base is involved in titration, we can use what? Methyl orange. Okay, that point we have to keep in mind. And second theory is what now? Acid-base indicator theory, quinonoid theory. Quinonoid theory. According to this theory, the acid-base indicators exist in two tautomeric forms having different structures. The two forms will be having what? Two different structures, and they are called tautomeric forms. The tautomeric forms, all these we'll discuss in organic chemistry. For time being, remember that if you take substance A and B, okay, within molecule A, suppose one H plus proton transferred from one atom to other atom, the same molecule. Suppose it is molecule here. Here from one atom to other atom. From one atom to other atom, what is happening here? The H plus is transferred here. The transfer of H plus from one atom of molecule to other atom of molecule. Then we got B, another structure B we got. Now structure A and B called what? Tautomeric forms. So the acid-base indicators exist in how many tautomeric forms? Two tautomeric forms. And the phenomena is called tautomerism. Tautomerism. That all we'll discuss in organic chemistry. But I am being remember that in one tautomeric form, when hydrogen ion, H plus ion or proton transfers from one atom to other atom in the same molecule, the new structure will be developed. New tautomeric form will be developed. That is called what now here? Tautomerism, and that forms called tautomeric forms. According to quinonoid theory, the acid-base indicators will exist in how many tautomeric forms? Two tautomeric forms having different structures. The two forms are in equilibrium with each other. The two forms will be in equilibrium. According to this Ostwalds theory, what happened? The undissociated molecule and its ions will be in equilibrium. Ions and molecules will be in equilibrium. But here in quinonoid theory, the two forms, what are the two forms? Tautomeric forms. The two tautomeric forms will be in equilibrium. One form is termed benzenoid form. One tautomeric form name is what? Benzenoid. And the other form is called quinonoid form. Quinonoid form, benzenoid form. So how many tautomeric forms here? According to quinonoid theory, two tautomeric forms. First one is what? Benzenoid. The second one is what? Quinonoid. Quinonoid. See here this one? It resembles benzene molecule. No? This molecule is what? Benzene structure here. Now here, this carbon is having one free bond here. This carbon is having one free bond. Remaining alternate double bonds, you see? Double bond, single bond. Double bond, single, double, single. So it is what? Benzene structure. The benzene type of structure is called benzenoid form. Benzenoid form. Here one free bond is there, one free bond is there. Now it will be in equilibrium with what? Quinonoid form. Quinonoid form. In this quinonoid form, C double bond will be there here. At the other end, C double bond. Here C single bond, C single bond. It is benzenoid form. Here alternate double bonds there, like in benzene molecule. But here alternate double bonds not there is, check it here. Double bond, single bond, again single bond. Double bond, single bond, again double single bond. Within the ring, here alternate double bonds not there. So the double bond is outside the ring here. Double bond is outside the double ring. So generally, bond CO bond, bond C double bond O, bond C double bond O, bond is called ketone, ONE. So ONE means quinone. So quinonoid form it is, quinonoid form. Here parallel double bonds you see, double bond parallelly present. Okay, it is quinonoid form. This one, benzenoid form. So quinonoid and benzenoid forms are what in equilibrium with each other. They are in equilibrium with. Okay, they are in equilibrium with each other. Okay, ma? So next one here. Next, the two forms have different colors. Benzenoid form has one color. Quinonoid form has one color. Then the color change is due to the interconversion of one tautomeric form into other tautomeric form. Tautomerism means what I told you. What will transfer from one atom to other atom? Proton will transfer. Due to transfer of proton within same molecule from one atom to other atom, the new tautomeric form is formed here. So due to transfer of proton within the molecule from one atom to other atom, the color change occurs. Structure will be different, color will be different for these two forms. Next point. One form mainly exists in acidic medium and the other form will exist in basic medium. Alkaline medium meaning what? Basic medium. In basic medium, one form will be there. In acidic medium, one form will be there. Next. Thus, during titration, the medium changes. Medium means what? Acidic medium to basic and basic medium to acidic medium. During titration, the medium changes from acidic to basic and vice versa. That means what now? Acidic to basic and basic to acidic, the medium will be changing. The change in pH converts when acidic medium is changed into basic medium, pH will change or not? pH changes. The change in the pH value converts one tautomeric form into other tautomeric form. How one tautomeric form will change into other tautomeric form? Whenever acidic medium is changing into basic and basic into acidic, the pH value will be changing, and due to changes in pH value, one tautomeric form changes into other tautomeric form, and thus the color changes, and the color change occurs. Now this is what now a benzenoid forms. Here alternate double bonds. See, double bonds. Okay, so it is benzenoid form. Now here in this case, what now here? Quinonoid form. C double bond. Yes, C double bond. So the C double bond form is what? Quinonoid. So benzenoid and quinonoid. Oh, phenolphthalein has benzenoid form in acidic medium because phenolphthalein itself is what? Acid, na? Phenolphthalein is itself weak acid. We know that. As it is weak acid, its main basic form will be benzenoid form. What is the basic form of phenolphthalein? Benzenoid form. The benzenoid form will be existing in which medium? Acidic medium. Because phenolphthalein is itself acid, na? So in acidic medium, it will be in which form? Benzenoid form. And thus, it is colorless. The benzenoid form of phenolphthalein is which colored? Colorless. The benzenoid form of phenolphthalein is colorless. While it has quinonoid form in alkaline medium. In basic medium, the same phenolphthalein molecule will get which structure? Quinonoid structure. That's why the color change will go to pink color. Means from colorless it changes to pink color. From colorless it changes to pink color. Now, methyl orange has quinonoid form in acidic solution. Now, phenolphthalein has benzenoid in acidic medium, na? But methyl orange has quinonoid form in acidic medium.